It's a great pleasure to have Paolo Luchini from Università di Salerno and talk about logarithmic profile of the mean turbulent velocity, recent developments about its universality. Thank you, Paolo.
Okay, thank you for the introduction. So, as the title says, I want to talk about some, say, modification of a logarithmic profile. But before that, I will give a general introduction to what the logarithmic profile is, because I'm told that maybe not everybody sees in the same way here. So we can start slowly, and if I am too slow or too fast, just tell me. Okay, so let's start very slowly with what is the logarithmic law of turbulence. So it's something in a sense similar to the Kolmogorov spectrum, in the sense that it is based on dimensional analysis coupled with the choice of what the governing quantity is. And in this case, the governing quantity is the wall shear stress. And so, a bit like in Kolmogorov law, the dissipation determines the spectrum. In a near wall flow, the wall shear stress determines the mean profile distribution along the normal to the wall. It's not a mathematically provable result, it's a guess in a sense, but it works very well in practice. And again, in this sense, it is similar to what happens for the Kolmogorov law. I won't talk about any complicated mathematics here. It will be mostly additions and subtractions, but we will try to get something out of it. So these laws must be intended as approximations. One should not try to be too precise about them because it would lead to contradictions. But we would be happy enough if the deviations go to zero when the Reynolds number increases. And anyway, the logarithmic law is basically the most accurate practical result that we have about turbulence. Everything else is even more hand-waving than this. And so it is taught in basically all books. But despite this, and despite the fact that it was discovered a century ago, there are still today discussions about it. And this is the reason of this presentation. So, again, let's start simple, and even in laminar flow, the simplest examples that you find in these textbooks are those where the variables depend on only one coordinate. And so we will focus on conditions where the statistical means of quantities depends on only one coordinate. And when this is true, and if we assume that these statistics exist and that we can talk about them, basically, the continuity equation reduces to just one derivative equal to zero. And since the velocity W here is a normal velocity, since it is zero to wall, it means it is zero everywhere. And for the same reason, from this equation that says that pressure plus something is constant in the direction normal to the wall, basically we can differentiate this and decide that the pressure gradient is constant everywhere, so it is just a constant. And then the remaining equation can be integrated once with respect to Z, and we get the balance of stresses in this particular case of flow depending on only one variable, where there are names that are usually given to these things, so we need to use these names. And so the classical stress, it becomes viscous stress in order to distinguish it. And this correlation of velocity perturbations, these primes are the fluctuations of the U and V velocities, becomes the Reynolds stress. And the sum of the two, in lack of a better name, is the total stress. And it is just a linear profile, depending on the stress at the wall and the pressure gradient. Now, the equivalent of this in laminar flow is just basically one flow for each of very few possible geometries with two walls. In turbulent flow, it still contains a parameter. I mean, this is not an equation for which we can obtain anything because it contains two variables and one equation, but it is a strong constraint on those variables. And what is left is basically a one-parameter family of possible solutions, where the parameter could be thought as the pressure gradient or the wall stress. So to make it non-dimensional, we use a Reynolds number based on the wall stress, this Reynolds tau, which will be the important parameter in all that I'm going to say after this. So we will parameterize everything in terms of Reynolds tau.
Excuse me.
Yeah.
No, I understand the Z is the direction between the
Yes.
walls, yes, and X is the direction where there's.
Whenever it's tau.
That term PXZ?
It's a multiplication, x times z.
No, I understand.
It's just the integral of this.
Yeah, no, I see that, but so that's like hydrostatic pressure or something.
No, it's not hydrostatic
No, but
pressure.
sort of why
I mean,
why it depends on what.
Do you agree on this equation?
Yes, no, I know that. I know.
What is the integral of this with respect to z? This is a constant. It is z
So, I'm
times
sorry,
px.
okay, you're saying pressure. Well, okay.
So basically, the total stress will be a straight line decreasing from something at the wall to the inside with a coefficient, pressure gradient is negative.
Okay, yeah.
We will see it just in the next slide.
Okay, I think I see.
We will see it very soon in the next slide.
PX is constant. That's what.
Yeah.
Do you need Z averaging over the PX?
Yeah.
That would then get you out of this.
Everything here is averaged. I mean, this is the average W, the average P, the average U. Primes are fluctuations.
You need the average of PX.
It's already averaged. I mean, P is the average. I'm using letters without anything, just for the average.
Yeah, no,
Okay, all right.
my confusion was.
This was it. Okay.
No, that wasn't it, but it's my.
But already it's P OH, it's PX, which is OH, because P is a function of X. It is dP over dx, which is a constant.
Yeah.
So
No, that's what he's written, right? Yeah, when he says.
It's still average.
but only when you have. Yeah.
Anyway, this will become clearer. So what can we do with this? If it was laminar flow, we would have a parabola for quasi flow, we would have a straight line for wet flow, and in pipe flow is also a parabola. And more generally, even if a boundary layer is not really depending on only one variable, it is quasi-parallel. So most of this also applies to the boundary layer. And this is why I put it in this. And in the computational fluid dynamics community, often these are referred as canonical flows because are the simplest one to simulate in addition to all this. And so are the flows on which you find simulation data, basically. So these are the canonical flows that you want to be interested in. And these are the actual turbulent flows. These are not hand-drawn. This is what actually happens to the velocity profile when the flow is turbulent. And so quasi flow becomes like this. Pipe flow is slightly different, it's slightly more pointy. And wet flow becomes this sort of S. And this is in actual scale at Reynolds tau 1000. Of course, it will change with Reynolds, but these are the actual turbulent flows, just to give you an impression of what we are talking about. So if we focus on the stress, what we were discussing before, so this total stress that is just a linear function is this straight line. And what is important is that the Reynolds stress is very often close to it. Basically, the difference, this red line is Reynolds stress, and the difference is viscous stress. So as soon as you go far from the wall, the viscous stress becomes very small, and the Reynolds stress basically lies on top of this straight line. So we basically know how the Reynolds stress behaves once we are outside this region. And again, these regions have names. We will use these names later in more details, but you can start to see here what kind of different regions we will discuss later. So basically, the first idea of this kind was in Prandtl's times, and was the idea of the mixing length. So what Prandtl said was that when you are in this region where basically viscosity is negligible and you have some Reynolds stress tau r, and you want to connect it perhaps to a velocity gradient, if not else by analogy with what happens in a viscous flow where there is a relationship between Reynolds stress and the velocity gradient, but you want to do it without viscosity, then this is dimensionally the only possibility. You must have some length, something here with the dimensions of the square of a length that connects the stress to the square of the velocity gradient. And if again, you know nothing else than the distance from the wall, the only thing with the dimensions of length is the distance from the wall. And so you assume that this L is proportional to the distance from the wall. And basically, you can then invert this and get du dz out. And if we are near enough to the wall that the stress is almost constant, so we are on the left side of the plot that I was showing before, the integral is just a logarithm. And so we get that the velocity profile is proportional to the logarithm of the distance from the wall. And of course, this is not true for very small z, it's not true for very large z, but there will be some intermediate region in which this is true. And this was basically Prandtl's idea. And this was modified later, but this constant that appears here is now called von Karman's constant, because von Karman worked on this after Prandtl. And this square root of wall shear stress is an important parameter that, again, we will see often, is something which has the dimensions of length, because this is the square of a length, basically, of a velocity. I mean, this is a velocity, this is the square of a velocity. So it has a name, it's the shear velocity. And one of the reasons that it is important is that from this equality, we can see that if U prime and W prime are of similar order of magnitude, this will also be the order of magnitude of both. So again, in terms of orders of magnitude, in terms of typical scale, the typical scale of the fluctuation is U tau. And this is another reason that it is important, yes?
So the mixing link is working a kappa z for which range z?
We will arrive at that. This was Prandtl in his time. I'm going a long history, we will arrive at that.
So, but even in Prandtl, it says for z from 0 up to something?
Was, well, from a minimum to a maximum, because it cannot be true at 0, it would be infinite,
Yes.
and it cannot be true at the center. So there will be some range limited on both sides. Value
Kappa in red.
is the proportionality constant here. So this length has to be proportional to the length to z, and the constant, I call it kappa.
But we don't know what it is in real.
We don't know what it is yet, but most of the discussion will be about its value.
Okay.
So the classical idea is it is about 0.4, but the details can get complicated.
No, he called it von Karman.
Yeah, because
So the modern version of this is more precisely founded on a separation of scales. So I mean, by modern, I mean 1940s. Yeah, maybe.
Mechanics.
So basically, we can identify some typical scales. And once we have identified this typical velocity, nu over this velocity is a length, and is a length that contains viscosity in it. So we call it viscous length. It will be some typical length for where the viscous effects are important. And of course, another typical length is the height of the channel, or the half height. So let's say that h is the half height of the channel. And then this ratio h over L happens to be the Reynolds number, because if we just replace this definition here, this is the Reynolds number, which means that if we take larger and larger Reynolds number, these two scales become farther and farther from each other. So we have a separation of scales in this problem, and we can discuss what happens on the scale LV and what happens on the scale H as two separate limits. So this is basically the origin of the, let's call it, modern interpretation. And if we go back to the picture, we can look at those layers starting with laminar flow. So in a boundary layer, let's talk about the boundary layer. Typically, we are used to distinguish an inner and an outer layer, but actually there is also an even smaller layer where the profile is just constant. And so it's just linear, I mean. And so it is not usually emphasized very much, but still it exists. Near the wall, everything is just linear here. But when we go to the turbulent case, there are 4 layers. And this is important for what we are going to say afterwards. So what happens is that there is, as always, an implicit flow. There is something similar to the Prandtl boundary layer, except that there are again, more unknowns than equations. So we have the von Karman integral formulation, but then we need closures of different types if we want to describe it. But then when we go closer to the wall, we have this logarithmic layer that we'll be interested in, where basically Prandtl's missing length works. And also, even nearer, we still have a viscous layer. So there are 4 different layers that we have to distinguish here. In the logarithmic layer, we will have something like Prandtl, suppose it would be. But we will get at it from basically from above, from below, from the other layers.
Can I ask a question? I mean, my picture is that, you know, the boundary generates multiplicity.
Mm-hmm.
So why is it that I still have a laminar layer close to the wall? Because I would think that that's where most of the vortices are.
Well, I mean, I call it viscous layer. To call it laminar layer could be ambiguous. I mean, what happens is that it is dominated by viscosity. So
Yeah,
it's not stationary.
But you're not saying that the profile is linear, right?
The profile is linear, but not necessarily stationary. It is fluctuating, but linear.
When you say it's dominated by the fight between viscosity and production, high production, high dissipation?
No, there is nothing special
No,
that
but what
happens
I'm
there,
saying is
except
that
that there is some
like-
velocity above.
Like shear.
And so it's
that's
like
where
wet,
the-
basically, but with non-stationary velocity.
Maybe it's a question about the buffer.
No, that's the red one. Are we talking the green or the red?
Statically. Okay, but maybe this is, okay, I guess this is the average, right?
Yeah, everything is average. We only speak about averages. But again, this is just a picture. If we, and something that I want to emphasize is that it took me years to realize this, but when in the meteorologists, this is my current here, when the meteorologists speak of the atmospheric boundary layer, they actually mean this layer, if I'm not wrong.
And they mean more than that. There is a log layer, and then there's also the layer above it.
Yeah, but still, I mean, in the layer above it is often not clearly identified.
I would say normally our representative boundary layer we would have both that inner layer and log layer.
Okay,
How long did it take you to work on that?
sorry?
The atmospheric boundary layer with the log layer?
Well, I mean, it's often described as something that is just driven by the shear of the wall.
Yeah, we have to have an explicit molecular parameterization boundary layer. We do the explicit log layer as part of parameterization, and then we move some of the non-linear diffusion to the inner layer. So we put the log layer in analytically to the parameterization, and then we have a other layer controlled by non-linear diffusion, which depends on stability.
Anyway,
But just
You need a real expert on that. I think pretty sure that's what's done, but you need a atmospheric boundary layer expert here. Already got some in data.
Just to be totally clear, your viscous layer on the right is just so thin it's invisible. That would be trying to work with it.
sorry?
Your viscous layer.
The viscous layer, yeah, it's not visible on this scale. The viscous layer is so thin that you don't even see it here.
Yeah.
It's just the black line is a viscous layer.
This picture doesn't see it.
How much of the inner layer in the turbulent case is described well by the log?
Well, we will arrive at quantitative things later, yeah. But I'm just describing what the pieces are. So let's continue with this modern foundation. So we have identified these scales, and we can precisely identify all the parameters in the problem, basically, which are the height, the viscosity, and this U-TOR, which is representative of the shear stress. So there are no other parameters. The velocity, whatever it is, it will be a function of z and these three parameters. So we could try to make dimensionless groupings of these parameters, and we would arrive at two possible dimensional groupings. But if we now introduce the separation of scales, then we can suppose that when z is much smaller than h disappears here. Basically, the velocity becomes independent of h. And if this is true, now there is only one parameter. And so we can write the dimensionless velocity as velocity over u-TOR. And we can write the dimensionless z as this combination, which is a sort of Reynolds number based on z. And they are often denoted with this plus notation, and they're called wall units. So this is the velocity in wall units. This is the height in wall units. And basically, this means that there is a single universal function f that we may know or not know, we may be able to calculate, we may be able to measure, but once we know it, it's just one. So even if we determine it empirically, we know that there is only one possible f. And in the opposite case, when z is much larger than the viscous length, basically we neglect viscosity. So we will need to build some dimensionless velocity in terms of other parameters, with an additional important consideration that since we don't see the wall anymore, we have basically Galilean invariance. Velocity plus the constant is just as good as the original velocity. And this means that we cannot speak of velocity as velocity relative to the wall. We have to make it relative to somewhere else. And so we make it relative to the velocity far from the wall. So the difference between capital U, which is the velocity, say at infinity in a boundary layer or at the center in a channel, anyway far from the wall, minus some universal function, well, this difference is a universal function. So capital F will be the universal function in this defect layer. It is called defect layer because capital U minus U is the defect in velocity. So the defect in velocity is universal function of basically z over h, which is the dimensionless z that we can construct with these parameters. So we have two universal functions, one working from the outside, one working from the inside. And then there will be a region where these two layers overlap, where z is simultaneously much larger than LV, but much smaller than h. And when we are here, velocity must be independent of both, h and u. And the only way to do this with a velocity that is still translation invariant is by saying that the derivative of velocity, which is translation invariant, is proportional to u-TOR over z with some constant. And if we integrate this, we get again Prandtl's logarithmic law. So we arrive basically at the same result, but as the matching of two layers that arrive from above and from below. And these are, of course, the same constants as before. This is again from Karman's constant. Actually, the inverse of this is from Karman's constant because of how it was defined. We have another universal constant here, capital B. And there is an important bit that since this is independent of the height of the wall, it must also be independent of the shape of the wall, basically, because we don't see the other wall. So this law must be universal, which means that both the wall law, the small f, and the logarithmic law don't see the other wall. And so they must be the same in any geometry. This is what is meant by universality. So if the assumptions before this are true, then the result must be universal in the sense that it is independent of geometry. In a round pipe or in a flat, yes, in a round pipe or in a flat wall, you get the same.
It's a question of curvature.
Still
I mean, it's like a boundary area. Near the wall, the curvature is invisible.
Well, it depends on the ratio of my height, but all right.
The curvature is on the scale h.
That's what basically we're talking about smooth pipe versus not smooth. So that's basically smooth.
This is, yes, the wall is absolutely smooth.
Means that it
Roughness is a completely different chapter, but here all walls are smooth.
So yeah, because for roughness, I mean like maybe there is curvature, not in the pipe, but in the wall, which is to be comparable, not to the H, but comparable to the
Exactly.
G plus, whatever, because there's complete.
Exactly. There is a whole chapter about roughness where LV is the important scale. So if you have roughness on the scale of LV, everything changes. We are assuming that does not happen.
Even in this region? See, why does roughness matter if you're on scales much larger than LV? Assuming that LV.
Because it will change small f. And so it will change basically capital B, which is the limit behavior of
So the
small f.
constants, but all the arguments are the same.
Yes, the arguments are the same. The values are different. But I will stress this universality because not all people agree on this, and this will be basically what we want to discuss later.
Paolo, am I right? Saying that I think the Millikan had a slightly different.
No.
I think
Yeah,
he had
the
the
layers.
concept,
Oh, yeah, you can arrive at this in different ways. You can say that you take the derivative first, or Millikan started with the logarithm directly. There are different ways to explain this in seminar.
What I remember is that his ordinary derivation is matching derivative, actually. Yeah. Okay. Anyway,
It's a
yeah,
great
no, that's
one.
mine. Yes.
Okay, so let's go back to our layers. This is an actual velocity profile with the layers on top of it. And again, the viscous layer is barely visible, as it was in the previous plot. It becomes visible if you use a logarithmic scale. And this is why very often you see this kind of plot in a logarithmic scale. So this thin viscous layer invisible here is this region, except that really here the velocity profile is a straight line, and it doesn't look like a straight line in logarithmic coordinates. So we lose this information. This is really a straight line. Then there is something in between where basically we have small f, which is a universal function, but in principle we don't know it, except that we know that it is always the same. Eventually it will become logarithmic, and even further it will become something that depends on the other wall, that's capital F, it depends on the actual height of the channel. So we will concentrate on this region, but this region is actually the overlap of small f coming from here and capital F coming from here. Okay, so just to make the analogy with the Kolmogorov spectrum, they are both based on the identification of one important governing quantity, which for Kolmogorov is dissipation, and for the log layer is wall shear stress. And there is one independent variable, which here is wave number and here is the coordinate. And then you want here the energy spectrum, here the velocity profile, and basically dimensional analysis does the rest. So they are both conjectures in the sense that we are conjecturing that this is an important quantity and then this is important quantity, but the rest follows. Okay, so we are out of 1940 and this is today. And when you go to discuss these things with colleagues, this is what happens. So somebody will say that it's not a log law, it's a power law. Something will say that kappa is not really a constant. And so somebody will say that actually this has to be true because it's simple. And what I will try to add to this is that if you add the correct higher order correction to it, then you get a basically 1 order of magnitude better fit with the data. And that to me means that this is the correct correction.
And then all those people will stop fighting.
They didn't.
They'll keep fighting.
So we will see.
They should stop.
They should.
BNNP. Paolo, what is BNNP? Are these specific?
Well, we will have. It does mean something. Okay, so the value of kappa. I mean, rightly you asked about what is kappa. So the value of kappa has been the object of investigation since Prandtl times, and basically Nikuradze in Prandtl laboratory set up some big experiment in order to measure this velocity profile. And the first finding was that actually a logarithm was better than the 1/7 power law, which was our competitor in that time. So it was definitely in favor of a logarithm, but the precise value of kappa is sort of subject to interpretation. You can draw different straight lines to this. Even Nikuradze had more than one straight line as the candidate for the slope, which would be kappa. So this chase started then and is still going on today. And to give you an idea, there are some big laboratories that are after the value of kappa. And so one was the Princeton superpipe built about 20 years ago, which is a large wind tunnel in pressurized air that can work at 250, at 240 bar, 140 times the atmospheric pressure. And it can reach a very high Reynolds number. The problem with it is that basically you compress a very large Reynolds number in a relatively small wind tunnel, but then also the space available for measurements is small. And so there have been discussions about how reliable eventually the measurements are, but they are the only measurements that we have at this Reynolds number today. So it was a very important achievement. And more recently, this object has been built in Italy by a European consortium, and it is a 110-meter long pipe of almost 1 meter diameter. Of course, very straight, very smooth, everything very precise in order to get this velocity profile as precisely as possible. And experiments on this are still ongoing. So from time to time, basically it is managed as a facility. People rent time there and go to make their own experiments. And so we have some results from Ciclope, but not maybe the best ones that we have in future. And in Japan, they have a large facility, which is not in principle a research facility. It is in the Metrology Institute. It's basically a very large pipe used to calibrate flow meters. But since it is a very precise, very large pipe, they have used it for this kind of experiments. And there are some very interesting measurements that arrived from this facility in 2015, just to collocate this in time. So it is really ongoing. And I don't have a slide for the numerical efforts, but there is a parallel effort in numerical computations in order to get simulation at higher and higher Reynolds number. I think the record was a few months ago at 10,000. Until a few years ago, we had 5,000. And there is one other difference. All the experiments are in round pipes, and all computations are in plane channels, except for some computations. But I mean, the highest Reynolds numbers are in plane channels. So we have to be careful there. So where is the problem? Why we don't succeed in getting a very precise value of kappa? Well, of course, since it is the coefficient of the logarithm, basically one possibility is just to take the derivative of the logarithm. And if u was really a logarithm, this object would be a constant. So we would hope that this logarithmic derivative of velocity would reach a plateau somewhere and before and after it is something different, but somewhere here we read the value of kappa, and it does not. It is more, this is the kind of result that you get. We are almost there. I mean, we can see that it must be in this neighborhood, but it's difficult from here to get a single precise value of kappa. And the other difficulty is that if you compare different geometries, so here I have 3 simulations. I'm mostly plotting simulation data because they are smoother. I mean, the error in experiments is more oscillating. So here we can see better, but they are very close. Simulations and experiments in this business agree completely with each other. So here we see 3 simulations at Reynolds number 1000. One is wet flow, one is plain Gaussian flow, the other is pipe flow. And again, they are close, but not so close. And if we take the derivative, the one that need to be a constant, well, these are the 3 cases. And it's quite difficult to get a single constant out of these 3 curves. So these are the 2 big obstacles. Basically, the variation with Reynolds number, actually the variation with Z, is not so logarithmic as one would like it to be. It is close to a logarithm, but not precisely a logarithm. And there is some dependence on geometry. The curve in different geometries do not superpose on each other. And even if we wanted to extract something, it would be different. And so many people have concluded that probably the logarithmic law is not universal, or if it is universal, at least the value of the coefficients is not universal. And some have concluded that it will be logarithmic after maybe 10 power 4, so that we don't see it yet. And both of the above is a third possibility.
I mean, it is another maybe very nice question, but I mean, mathematically, you expect purpose should have an effect on the pressure at the wall. So why would this be universal unless you take it down?
Well, because, I mean, we will talk about pressure in a moment, but the whole assumption behind this is that only the stress at the wall is the leading quantity.
But the stress depends on the pressure also.
That's what I will say.
Okay.
So let me say.
I agree.
But I mean, I'm the only one to say it. So,
What do you want to say?
because in that group of people that were citing each other.
Yeah. Oh, and what are you the only one to say? What is your
That pressure is also important, and not only the shear stress.
I agree with you.
Okay. I hope I will conquer somebody here. Okay, so some quotations from the literature, just to be more precise about what people say. So one of the beginners, but actually very active in propagating his theory was Barenblatt here in Cambridge, actually. And basically, he had a long argument to maintain that a power law is more appropriate than a logarithmic law to describe basically this same situation. He was not too aggressive. I mean, he just said that the experimental confirmation is just as good for both. So others have been more aggressive in this, but he was definitely against the logarithmic law. And other people have been saying that the von Karman coefficient in channel flow is smaller than one in the boundary layer, and in pipe flow it is higher. So basically that kappa changes with geometry. And this is a relatively well-known review by many people in 2010. It's a long review with a lot of experiments discussed. But basically, these are the conclusions that for pipe flow, the constants appear to be 0.42 and 5.6. These are the kappa and b that we had before. For the boundary layer, kappa is between 0.38 and 0.39, and b is 4.2. And for channel flows, kappa is more uncertain and between 0.37 and 0.59, and there was no clear b in this specific sentence. So basically, again, that both kappa and b are not the same in different geometries.
There doesn't seem to be very much variation in kappa over that size, obviously, but when you've got, well, 384 and.
Yes, this is a large variation.
Sorry?
I mean, this is a large range. This is this what you were saying?
No, I'm a bit part, you're saying that all those values of kappa look rather similar.
Well, no, it's not. It's not. It's not so similar.
High standards.
It's not so similar because I mean, from this is a straight line, and when you get the friction coefficient out of this, you are in a sense extrapolating the straight line. So a small change in kappa actually has an important effect.
Now, listen, I'm an outsider in this. The impression I got is all those numbers are rather similar.
But anyway, if you are glad with 0.4, Prandtl already said that.
Yeah.
The discussion is whether it is what the next digit is.
So 100 years worth of fun. 100 years per digit.
Yeah, 100 years per digit, exactly. Okay, yes, you can say that this is not a relevant purpose to get a precise value of kappa, but there are people who are interested in getting a precise value of kappa.
If it exists at all.
Yeah. What did you say?
If it exists, I mean, you say, well, other people saying it's theory.
Well, I mean, it exists for a parallel channel.
Oh, yeah.
Whether your actual situation is close to a parallel channel is a different question.
I don't really know anything
Paolo,
about this.
what are all these little circles at the top?
Yes, yes. We will skip many of those. I was prepared to skip many of those. So, but yes, if you want to go on, we can.
We switched the clock to 2, so.
That's why.
Logarithmic.
So, okay. So what can we do to make this better? Well, one idea is relatively old, and it is that you can combine the inner and the outer layer in one uniform formula by the classical recipe of summing the inner and the outer expression and subtracting their common behavior. And when you do this, you arrive at the idea of cols, which we are still in 1956. It's modern as well. Where basically you can write the velocity as the sum of that universal F that we had before and the universal G, which is related to capital F, but it's easier to write it in this way. And so you have, again, two universal functions, a function of Z plus and a function of capital Z. And this takes the name of law of the wake, which is how Coles called it for several reasons. And we know from the definition that it has to have this property. So basically, when Coles did this, he was focusing his attention on boundary layers. And basically, by comparing different experiments, he arrived at the idea that this capital G has the same shape now in different kinds of boundary layer, which means boundary layers and a different pressure gradient. And so that it is, in a sense, universal in a bigger sense than we were saying before. But anyway, what I want to focus on is this shape, because then we are not talking about this, we are talking about parallel flow. And so there is the question whether something similar exists in parallel flow. And this has not been taken seriously for a long time. Maybe one reason is this sentence in Schlichting boundary layer theory, which says that excellent agreement is obtained not only from points near the wall, but for the whole range up to the axis of the pipe. So basically what Schlichting says is that the logarithm naturally is good up to the center, and so doesn't need any correction. Basically, if there was a capital G, it would have to be 0. And for a long time, it has been considered to be 0. Hardly any of those papers that I was mentioning before introduces a capital G, introduces an outer layer correction. There is only one example that I know of, which is this paper by Prandtl in 2007, where he tried to extract the correction by subtracting basically the logarithmic law from some measurement data. So he had these plots which are similar to ones that I will show afterwards, but basically his conclusion was that the result is sensitive to the precise log coefficients, and so one cannot determine the other, basically. So if you assume the coefficients, you get a shape here that if you know neither, you have one equation and two unknowns again. But this is an important clue. And so now let's take the layer structure again. And if we look at the laminar flow closer, then in laminar flow, actually, we can tell more than this is a straight line. We can tell that there is also a quadratic term with a very simple coefficient, which is a pressure gradient. Basically, it's the integration of the equation that I had in the very first slide. And if we write this in the dimensionless variables in the wall units that we are using for the turbulent flow, a Reynolds power -1 appears here. And so this clearly shows that it can be interpreted as a beginning of some maybe asymptotic power expansion. We have a base term and a correction proportional to Reynolds power -1. So this correction has a double interpretation. It is the role of the pressure gradient, but also it is a lower order correction to the main result. So the question is whether it should also happen in turbulent flow. So this is the logarithmic law. Is there something proportional to pressure gradient and to Reynolds power -1 that we should add here? And I will tell you that there is, but I mean, this is one reason to suspect that there must be one. So let's try to build this correction. If we analyze again the argument that was at the basis of the logarithmic law, so it was in 3 points. One is that viscosity is small when C plus is large, because basically it is at the denominator in this expression. So small, I mean, probably negligible. The other is that the distance from the other wall is large and probably negligible when Z is small compared to H. And the third is that if this is true and we don't see the other wall of the side of the pipe, we don't even know what shape it has. But the pressure gradient is special because the pressure gradient is constant. So the same pressure gradient that we see in the outer layer, we also see it near the wall. In a sense, it propagates information all the way to the wall. And so the pressure gradient actually can act as a perturbation to the universal logarithmic law. So in a sense, we don't see the shape of our wall, but we see its pressure. And so this could be a useful starting point. And so if we now look at the derivation that I showed you before, so basically we have a conjecture, an ansatz to start with, which is that in the overlap layer, this quantity is dependent of both viscosity and height, and I add end of geometry as a consequence. And when we combine this with the fact that these two are negligible, dimensional analysis gives just one possible answer. Now, if we add pressure gradient, but we suppose that it is a small perturbation, then we can again suppose that the effect will be linear. If this is the beginning of a higher order correction, it will be a linear term in the pressure. And so if we assume that it is linear, there is again only one possible way in which it can appear in the equation, which is some constant times px over tau wall. This already has the dimensions of the inverse of the length. We want the inverse of the length. Well, no, we want, what did I write here? This is, yes, we want the inverse of the length because this is the derivative divided by velocity. And so this is the only possible inverse of the length linear in pressure gradient that we can add to the formula. And so we have basically one new constant here. So we integrate now. When we integrate the classical expression, we get the logarithmic law. When we integrate this new factor, we obtain a correction which, in addition to being linear in the pressure, is linear in Z. So basically, we get logarithm of Z plus constant times Z. And this constant has the Reynolds power -1 in front. And if we express it in outer coordinates, it doesn't have it, it has only capital Z. And we can recognize that this is exactly what happens, for instance, in a boundary layer, where the first asymptotic correction to the inner solution is the first term of a Taylor expansion of outer solution. It is exactly the same thing. And this dimensionless pressure gradient for the parallel flows, for the canonical parallel flows, actually is a constant for each. This number is 2 for pipe flow, 1 for quad flow, and 0, 1 for Chauzy flow, and 0 for quad flow. So basically, this G for geometry is a number for each. And everything else is contained here. So yeah, this is what I was saying. This makes sense in the sense of an asymptotic, in the context of an asymptotic expansion. And so now I will probably skip something. Yes, I must. So I will skip how, so how do I go forward?
You might not even have time to scroll through the rest.
Yeah, I wanted to click on that, but I cannot click here. So let's try to go forward. And what I'm skipping is how we can try to estimate this, but I will directly tell you what the numbers are. These are the constants that come out of estimating this law from basically all the data that I could collect. And we can look at how well it fits. And we can do it if we subtract the correction from the actual data and compare it with the logarithmic law. It's easier than the opposite. So basically, this was the first picture where we have this thing that is not flat enough. And when you subtract the correction, it becomes this. And so it is now much closer to having a plateau. And we also see more or less where it has a plateau. One of the questions were, what are the limits of this range? Is this. So basically, we can have the logarithmic layer between Z plus greater than 200 and smaller than half of the height. This is more or less the range where the fit is good. And this was the second picture with these lines for different geometries, and they become these lines. And these are their derivatives. So now they do have a common slope.
But how come they do worse on the left side?
Sorry?
How come they do worse on the?
I mean, this is just the data, the data, this is just the data. And this is the data minus the correction. And this purple line is the logarithmic law. So instead of writing the data and the logarithmic law plus the correction, I'm writing the logarithmic law and the data minus the correction, because this makes the comparison easier.
Okay.
And these are the numerical simulations of Lee and Moser, the ones that arrived up to 5,000. This is without any correction, and this is with the correction. And in all these plots, the straight line is always the same straight line. I'm not fitting the coefficients. Those numbers that I showed before are the same in all figures. This is pipe flow. And again, this is the simulations at 1,000 and below. And this is without any correction. And this is with a correction. And I mean, you see some undulations, but it's also a relatively small Reynolds number. But if I drew the line here, it would be in another place. This is why from this data, people get a different number for kappa, because if you draw the best straight line through here, it would have a different number. And wet flow doesn't need any correction, and it already fits always that same straight line. And these are other experiments. These are experiments. Those are simulations. These are experiments. There is both the plane channel and the pipe channel. This is one of the few experiments done in a plane channel. Again, not exceedingly large Reynolds number, but already better than in the previous simulations, with some more wiggles. But still, this is without correction. This is with correction. And this is pipe flow without correction and with correction. And above all, the same straight line everywhere. And so since it's late, I'll go to my favorite one, which is this Japanese experiment with a very large water pipe. And this is without any correction, and this is with a correction. And you can hardly see any difference.
So the value of kappa here, is it the same for the boundary layers?
Yes, it's always the same value of kappa. In all these figures, I have that 0.392 that I had, and it is similar to what people ascribed to the boundary layer before. Yes.
But when you subtract, can you just tell us a bit more about each curve, what you subtract? Is it?
Is px z times the coefficient.
Yeah, but I mean, you don't have px, right?
I do. This is a pipe.
Okay, so in all
px
these
is
cases you have access to, so.
the G is a fixed number. In a single geometry, wall stress and pressure gradient are not independent.
So
They only become independent when you change the geometry.
I'm just trying to get a handle of how many things you're fitting. So there's kappa, which is a fixed number, right? Like,
Kappa is a fixed number.
and then,
I mean, I'm not fitting anything here. I only fitted once forever,
right.
kappa, B, and A1.
Once for every kappa and nothing else.
Once forever kappa, once forever B, once forever A1.
Yeah,
Then
that's what
I'm
I
not
wanted.
touching them.
How many constants? Kappa,
Three.
Three, okay.
But for all the experiments,
I understand.
I'm not
I don't wanna know
fitting
how
to
many
each
numbers.
case, yes.
And G was one. G was one.
0, 1, 2.
G, no, A1 is G is the geometry. Yeah, one of these constants is 1, and this is another strange
But
thing
G
that
would
could
be
not
also
happen by
from
chance.
two.
But yes, one of these constants is actually the best fit value is very close to 1, so I just put 1 for it.
Paolo, let me, you can do this, and of course, this is certainly different. I mean, you have also viscous shear stress contribution to the group layer. Of course, you know, all these geometry, viscous elements are the same, so you don't need any subtraction for that in the scaling. But the
No,
The
I
loop
don't
layer.
understand the question. What do you mean?
so you have in the loop layer, I mean, in the loop layer, you have two contributions. One is viscous, two small contributions. One is
in the
pressure.
wall layer, not in the log layer. The log
Loop
layer-
layer, you have two small contributions, viscous stress and the pressure.
No, viscous stress is big, pressure is small. They are a different part. I have
The
one main
loop layer,
contribution, which is a
stress
classical
constant.
log layer, plus a correction of order Reynolds -1, which is a pressure.
Okay, I can talk to you later.
Yeah.
Okay.
So I think I will basically stop here because I cannot say much about the rest. So there are other. So let's go here. So basically, what I showed you that this correction to the logarithmic law fits all the present data in all geometries with a single value, whereas, as I showed you, there are many now published articles that say that the value should vary. And in addition, the range of validity becomes much larger than it is supposed to be when you do not have this correction. And the range of validity in terms of Reynolds number becomes a relatively small Reynolds number, whereas some of the present theories are that you would only see something after, say, 40,000 or something like that. So you can do DNS at this Reynolds number, you cannot do it at 40,000. And I will stop here.
Other comments about one?
So what's to stop you going further? So
What's
this is absolutely fantastic. You in terms of that expansion of that. What's to stop you from going any further?
from data, because we are already at error in the data. I did try. So I did try to get an even higher order term, but you only get noise from the kind of data that you can see today. You will need much more precise experiments and simulations.
What does it depend on? Does it depend on the stress squared or something, or pressure squared?
On 1 over Reynolds square.
What was it? What was the term? Did it depend on the stress squared
Well, I mean, there is no,
combination or the pressures?
I mean, what I did try is to get a further term in expansion for a single geometry to start with.
Right.
And then it will just be 1 over Reynolds squared. I'm not even guessing what else it would depend on because I don't get it anyway. We will need much more precise data in order. I mean, for some time, I have some curves, but I don't believe in them. So
Okay. And what about can you put the curvature or guess difference between concave or concave?
well, this is, I mean, this is only for straight flow. So it's somewhere around pi.
That's not a real part, but just slightly bended one way
Or
or the other.
curvature in lengthwise, but that changes very many things.
So
It becomes quickly a very completely different flow
And
with
still
separation.
No, not before there was a rock, just very near the boundaries. Prevents. There's no guess.
Well, I mean, at leading order, this is true near any
That
point.
remains at least.
But the correction is different.
No, but that's okay, not just the leading order. But there is no influence then.
Well, the leading order only depends on the local shear stress. Except that if it separates, then it becomes.
No, it's not one before.
Comment concerning the Prandtl. Sorry, concerning the Warmblood. Even though he was a believer in the last minute about power law, but then he wrote an article in which he basically realized and mentions that yes, you do logarithmic, but it is the envelope of all the curves for many
Well, yes.
power law.
So in his
In some sense, he doesn't deny law, but he
No.
interpretation.
No, basically he says that it will become logarithm at very large Reynolds number. So it's a bit in the yes.
I use the word envelope. Because
Yes, so it is related to this.
This will later work with Jordan, that's my understanding.
So this is the Nikoradze experiment. And so one thing that Barenblatt noticed at the start is that if you separate the different experiments, which here are not separated, then you notice that actually the slope of each experiment is different from the common slope of them. And so he could fit a power law better to each individual experiment, but the envelope was a logarithm.
That's exactly what he said. That's what
But I mean, in a sense, you can connect one to the other because it has basically two parameters to fit. And so you can convert one correction in the other. What I think is different is that here you can also connect it to geometry. This was basically for a single geometry.
Another question is that maybe you did, but I didn't see it in the leaflet. The results. How do you most of the results from the super part of the results was Zagarola and company?
Yes, there is also one picture for that somewhere here. Yes, this is it.
Because when his result did not fit, he basically dismissed. So basically, he mentioned one of the article is like, oh, the reason their theory does not fit. Why? Because it's not there's roughness. And that's what caused some kind of like.
Yes, this is why the larger Reynolds numbers can be questioned. Yes.
Some kind of like.
So this is not the largest Reynolds number that they used. They went up to 500,000. I'm starting 100,000 here. But there was this question because basically the viscous scale in their experiment becomes incredibly small. And so both the tolerance to roughness and the size of a measuring instrument are a problem.
So you're basically the quantity, the pressure gradient divided by the wall shear stress is a new length scale that is units 1/length. Can you go way back to the beginning and just throw that into Prandtl's theory? Or?
Well, it's not a new length scale. It's 0, 1, or 2. It's a number for each geometry.
It has units of 1/length. Pressure gradient divided by
times
wall shear.
h px over tau is 0, 1, or 2.
Right, but so you're.
This is what is called the hydraulic diameter divided by h.
Yeah, I get that, but just going back to the original dimensional analysis arguments.
Yeah,
So in those,
Yeah, this
only
is-
H was
this
there.
is why Z comes in, because again, the only local length is Z. So. So basically, when you do it for the derivative, this already has the right dimension, which is the inverse of the length. And when you integrate, Z comes in front of it.
Right, I'm just thinking if you go all the way back to Prandtl, the first part of your notes.
That was a rougher version of what Millikan said afterwards. It's not conceptually different.
But it's an extra non-dimensional.
All I'm asking is, so if you just start with dimensional.
So
analysis-
maybe I understand what you mean. This is why it is important to qualify pressure as a small correction. Because if I just say that it is an additional parameter, I get an unknown function of a new parameter. If I say that it is a small correction, I impose that this function is linear. And then I only get an unknown coefficient.
Got it. Yeah, now I'm, yeah.
Well, it's not, okay, probably can't be, but, the transition to turbulence Reynolds numbers are different by factors of, between wet, wet and circular pipe and plain channel flow. But the reason for that is that one non-dimensionalizes pipe flow by the diameter, and one non-dimensionalizes plain channel flow by the half height. So naturally, when you wrote a G2 and G1 there, I wondered if that's not what's responsible.
That's just geometry. This is just circumference divided by area. That's hydraulic diameter.
Okay, and that's, okay, right, thanks. I'll ask you.
I'll see if the other question later on. Thanks, Paolo.
Okay. One more thing, if I can get to the end.
Yes.
Which I was hoping to click on it, but
There is one.
which is this. So if you can guess what this is, if not, come on April 5. Okay, thank you.
All right.
Thank you very much.
Since you're